Black holes do not just pull, they spin. And when something that massive spins that fast, it does not merely curve space around it. It drags space, physically, as if space itself were a liquid caught in a drain, pulled into rotation by an object so dense that the fabric of reality has no choice but to follow. Near a spinning black hole, there is a region where standing still becomes physically impossible. Not difficult, impossible. Space itself is moving. You are inside it. You move with it, whether you fire your engines or not. That region is called the ergosphere, and it may be the most useful place in the universe. Because inside the ergosphere, physics allows something that sounds like it should not be allowed. You can enter, steal energy from the black hole, and leave. The black hole slows down, you speed up, and the energy you extract is real, measurable, and, in principle, limitless. A black hole is not just a destroyer. It may be the largest battery the universe has ever built. To understand how this works, you need to understand why spinning changes everything. Most of the black holes we discuss in popular science are simplified versions: spherical, symmetric, non-rotating. These are described by the Schwarzschild solution, published in 1916. One boundary, the event horizon. Behind it, a point singularity. Clean, simple, and almost certainly not real. Real black holes spin. They spin because the stars that created them were spinning. When a massive star collapses, it conserves its angular momentum, the same reason an ice skater spins faster when pulling their arms in. The rotation does not disappear, it concentrates. Some black holes spin at over 90% of the speed of light. In 1963, a New Zealand mathematician named Roy Kerr sat down with Einstein's field equations and solved them for a rotating mass. The solution took the physics community by surprise, not because it was difficult, but because of what it revealed. A spinning black hole is a fundamentally different object. The singularity is not a point. It is a ring. The event horizon is not a sphere. It bulges at the equator. And outside the event horizon, a second boundary appears, one that does not exist around any non-spinning black hole, the ergosphere. The ergosphere is the region between the outer boundary, called the static limit, and the event horizon. It is not inside the black hole. You can enter it and leave, but while you are inside it, you cannot stand still. The reason is frame dragging. Every massive object drags space slightly as it moves. Earth does it, the Sun does it. The effect was confirmed by Gravity Probe B in 2011, a drift of 37 milliarcseconds per year around Earth, barely detectable. Around a spinning black hole, the same effect becomes overwhelming. Near the event horizon of a fast-spinning black hole, space is dragged so violently that it moves faster than the speed of light relative to distant observers. Not the matter inside it, space itself. The coordinate frame that defines here and there is in motion, and nothing inside it can resist. This does not violate Einstein. His speed limit applies to objects moving through space. It does not apply to space itself, which can expand, contract, and rotate at any speed. The same principle allows the universe to expand faster than light at its edges. Inside the ergosphere, you are carried along. Your engines are irrelevant. You move because space moves. To make this concrete, if you entered the ergosphere of a fast-spinning stellar black hole and attempted to hover, firing your engines at maximum thrust in the opposite direction of rotation, you would fail. Not because your engines are too weak, because the concept of standing still no longer has meaning. The coordinates that define your position are themselves in motion. Fighting frame dragging inside the ergosphere is like trying to swim upstream in a river that is moving faster than you can swim. Except the river is not water. It is space. The fastest spinning black hole measured to date is GRS 1915 + 105. a stellar mass black hole approximately 36,000 light-years away. Its spin parameter has been measured at greater than 0.98, meaning it is spinning at more than 98% of the theoretical maximum. At that rate, the inner edge of its ergosphere is spinning space at a velocity approaching the speed of light. That is not a theoretical object. It is a real black hole in our galaxy, measured by X-ray observatories. And it is, by the physics, an energy source of extraordinary magnitude. But, and this is the critical point, you can still escape. The ergosphere is outside the event horizon. With enough thrust in the right direction, you can exit. And when you do, you can take something with you. In 1969, physicist Roger Penrose proposed a mechanism for extracting energy from a spinning black hole. The idea is elegant, and within the framework of general relativity, mathematically rigorous. The process works like this. An object enters the ergosphere. Inside, it splits into two pieces. Think of it as jettisoning cargo. One piece is directed so that it falls into the event horizon on a trajectory opposing the black hole's rotation. The black hole absorbs it. But because the piece was moving against the spin, it carries negative energy relative to the black hole. The black hole's rotational energy decreases. The other piece exits the ergosphere. It is moving faster than the original object was when it entered. The excess energy came from the black hole's rotation. The black hole is now spinning slightly slower. The escaping object carries energy that was extracted from the spin of space-time itself. This is not theoretical speculation. The mathematics has been verified independently for over 50 years. A black hole can be slowed down, and the energy it loses can be collected. That leads to a number that is difficult to absorb. A black hole spinning at its theoretical maximum stores approximately 29% of its total mass energy in rotational form. For a stellar mass black hole of 10 solar masses, that is the energy equivalent of roughly 3 solar masses, converted entirely into usable energy. 3 suns from a single black hole. For a supermassive black hole at the center of a galaxy, the number stops making intuitive sense. The rotational energy stored in a billion solar mass Kerr black hole exceeds the total energy output of every star in the Milky Way combined across billions of years. The universe built these objects, and it built a mechanism to extract their energy. There is a second mechanism, more practical than the Penrose process, that accomplishes the same thing without requiring anything to fall into the event horizon. It is called super-radiant scattering. When electromagnetic waves, light, radio waves, any form of radiation, pass through the ergosphere at the right angle, they can extract rotational energy from the black hole and emerge amplified. The wave goes in at one energy, it comes out at a higher energy. The black hole spins down slightly. The wave carries the difference. This process happens naturally. Every spinning black hole in the universe is, in principle, radiating energy through superradiance, losing angular momentum to passing waves, photon by photon, interaction by interaction, across billions of years. In 1972, physicist Yakov Zeldovich proposed that the same effect could be artificially amplified. Surround a spinning black hole with a reflective shell, a mirror, and the waves bounce back and forth through the ergosphere, amplifying each time. The energy builds exponentially. This is called a black hole bomb, not because it explodes, but because the energy extracted grows without limit until the mirror is breached or the black hole stops spinning. No one has built a black hole bomb. The engineering challenges are beyond current capability, but the physics is sound. The energy is real. And there is evidence that nature has already built its own version. In 1977, Roger Blandford and Roman Znajek proposed that the relativistic jets observed shooting from the poles of active galactic nuclei, beams of plasma moving at nearly the speed of light, extending for thousands of light years, are powered by the same mechanism. Magnetic field lines threading through the ergosphere are twisted by frame dragging, extracting rotational energy from the black hole and channeling it into jets of extraordinary power. The jets of M87's supermassive black hole, the first black hole ever directly imaged in 2019, extend approximately 5,000 light-years from the galactic center. The energy powering them is drawn from the spin of the black hole itself. This is not a theoretical proposal waiting for confirmation. The Blandford-Zeneject process is the leading model for jet formation in active galaxies. It has been tested against observations for nearly 50 years. And it means that energy extraction from spinning black holes is not something humanity would be the first to achieve. The universe has been doing it for billions of years. We are only now understanding how. Here is what the physics confirms. Spinning black holes, described by the Kerr metric, possess an ergosphere where space itself rotates faster than light. The Penrose process allows energy extraction from a spinning black hole by reducing its angular momentum. Superradiant scattering amplifies electromagnetic waves passing through the ergosphere. The maximum extractable energy is approximately 29% of the black hole's mass energy. Frame dragging has been experimentally confirmed around Earth by Gravity Probe B. Here is what the physics does not yet tell us: whether the Penrose process or superradiance can be engineered at any practical scale, whether civilizations elsewhere in the universe have already found a way to harness this energy, and if so, whether the jets we observe from distant galaxies are evidence not of natural processes, but of engineering on a scale we have not yet learned to recognize. What happens to a black hole when all its rotational energy has been extracted, whether it settles into a perfect non-spinning state, or whether quantum effects intervene before that point is reached? We built physics to describe how the universe works. Those equations predicted that the most destructive objects in the cosmos, objects from which nothing can escape, contain a region where energy can be freely taken. The universe did not have to work this way. Black holes did not have to spin. They did not have to drag space. They did not have to create a region where the laws of physics permit extraction of energy on a scale that dwarfs every star. But they do. And the equations that describe them have been sitting in plain sight since 1963, waiting, like the energy itself, for someone to find a way to use them.